How the universe maintains its balance? Have you ever pondered about this profound question? What if I tell you that there is an elegant and beautiful link that ties together the symmetries of the universe with the law of conservation? But here is the real question. Who was Emmy Noether and how did she unveil this breathtaking connection that reshaped the way we understand the very fabric of reality? What is Noether's theorem and how did it bridge the gap between Einstein's general relativity and the principle of conservation of energy? Well, in this video I would be explaining you about Noether's theorem and how she provided the missing piece of puzzle, allowing Einstein's general relativity to harmonize beautifully with the principle of conservation of energy once again. I would be also talking about the best practices in learning Noether's theorem, what is the best book, and about a fascinating history how Noether's theorem actually saved Einstein's general relativity from getting violated by one of the basic fundamental laws of physics. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this new video on Noether's theorem. Before I go ahead, I would like to tell you that every new theorem, every new mathematical formulation, every new mathematical model comes out of necessity, comes out of a problem, comes out of a limitation which was not being reached by the earlier theorem. And Noether's theorem was not an exception. What was that problem that actually invited Noether to come and develop this profound mathematical formula? Let us first understand, coming up into the next part of our video. There was a problem in Gottingen University, and it was around 1915 that Albert Einstein has already formulated the general theory of relativity. But it caused a considerable stir at the University of Gottingen. The theory appeared to be at odds with one of the fundamental principles of physics, which is called the law of conservation. Consequently, there was a widespread concern and unrest among the academic community. It seemed that the theory did not adhere to a well-established physical principle which is known as a law of conservation of energy, which states that the energy can change forms but can never be destroyed. Total energy is supposed to remain constant. Now, there was a violation that seems to happen, and the entire Gottingen University with the top mathematicians were unable to solve this problem. Two of the world's top mathematicians during that time, David Hilbert and Felix Klein, was trying to solve, but including Einstein, they were unable to solve this puzzle. And during that time, they invited Emmy Noether to the University of Gottingen to investigate a puzzle. She resolved the issue head-on. Noether's theorem uncovered a hidden relationship between two basic concepts, symmetries and conserved quantities, that until then had been treated separately. But before understanding her deep philosophical work, we first need to understand what was the problem. What was actually the problem which invited all these great mathematicians, Emmy Noether, to solve this problem? Let us first understand, because without that we won't be able to appreciate and understand this problem. So coming up into the next part of the video, what was actually the problem with general relativity? Now, in the context of classical mechanics and including special relativity, there were well-established laws of conservation, such as the conservation of energy, conservation of linear momentum and angular momentum. These conservation laws were associated with symmetries in the underlying space-time. For example, conservation of energy arises from the time translation symmetry of the laws of physics. In other words, the laws of physics do not change with time. This leads to the conservation of energy. Conservation of linear momentum arises from the spatial translation of symmetry with the laws of physics. In other words, the laws of physics are the same regardless of where you are in space. This leads to the conservation of linear momentum. Conservation of angular momentum arises from the rotational symmetry of the laws of physics. In other words, the laws of physics are the same regardless of the orientation of your coordinate system. Now, we should remember during the time that we are talking about, when Einstein formulated general relativity, introduced a new understanding of gravity as the curvature of space-time, which is caused by mass and energy. Now, the theory was built upon a new geometry which is called the Riemannian geometry. However, it was not immediately clear how the principle of conservation holds in curved space-time. The problem was that general relativity did not have a straightforward global notion of energy and momentum conservation, unlike the classical or the special relativity theory. Instead, the equations of motion were described by Einstein's field equation, which were tensor equations involving the curvature of space-time. So here is the foundation from classical mechanics. Once we move into curvature of space-time, taking help of Riemannian geometry, the problem or the issue of conservation of energy was not very clear. Now, we should remember that it was around 1912 Einstein has been searching frantically for an expression for the laws of gravitation invariant under general coordinate transformation. Already with Marcel Grossmann, he has developed this, what is called the Entwurf paper, which is a German word meaning draft, with Marcel Grossmann, who was an expert in differential geometry and tensor calculus. As I have already explained in many of my videos, that Marcel Grossmann actually taught and introduced tensor calculus, which was not known to Albert Einstein. Now, he actually already has given a detailed development of tensor calculus and worked out the geodesic equation. He discussed at length the covariant balance equation for the energy, momentum and stress tensor density subject to external forces. Now, as you see on the left hand side of the screen, that he gave an explicit description of this T mu nu in terms of the Christoffel symbols, and noted that it is not a tensor but is something which is called a pseudo tensor. But it is invariant, obviously, under linear transformation. Now, at this point, we should remember that Einstein wrote his tentative field equation explicitly in terms of this pseudo tensor. Thus, from very early on, the gravitational energy momentum pseudotensor was in Einstein's mind an important ingredient of the theory that he was seeking. But this pseudotensor actually created a problem. What was that? Let us find in the next part of our video. In the two of his papers from November 1915, Einstein has already given a very general expression for the gravitational pseudotensor in terms of the Lagrangian density and found the correct gravitational field equations. As we all know that in 20th November 1915, 5 days before the publication of Einstein's famous relativity that contained the final form of the field equation, David Hilbert had submitted what is called in his Die Grundlagen Physik, or the Foundations of Physics, which was an attempt to axiomatize general relativity. Felix Klein compared Hilbert's energy equation and Einstein's conservation law, and Klein's main point was there was a disanalogy between Hilbert's energy equation and the conservation of laws in classical mechanics. So here is this picture on the right hand side, which shows the conservation of energy in terms of classical mechanics follows as a consequence of the equations of motions, but in general theory of relativity it is just an identity. What does it mean? It means that it is valid without requiring the equations of motions to be satisfied. So Felix Klein actually found out that comparing with Einstein's equation along with David Hilbert, I'm not going into those equations, there is something which causes a disparity, and you really cannot compare the conservation of energy compared to that of classical mechanics with that of general relativity. Well, this is actually the statement which Felix Klein made, that the above statement cannot be regarded analogous to the conservation of law. You can read it right at the bottom. He was not quite satisfied with the analogy that he was using. Further, he told this statement, after this, I can hardly believe that it is appropriate to characterize this. So he concluded with the note that he cannot actually believe in this. Now, in reply, David Hilbert actually agreed to Klein's comments about the lack of analogy between the energy equation and the conservation of energy in classical mechanics. He took this one step further by expressing his belief that no true law of energy conservation exists in general relativity, and claiming that it is possible to prove a theorem to this extent, to which Felix Klein told, it is possible to prove this theorem, to which Felix Klein told this, that I would be very interested in seeing the mathematical proof, to which you alluded to your reply. So this was actually Felix Klein's reply that he would be interested to do. But remember that such a proof would not be provided by Hilbert or by Felix Klein, but by Emmy Noether in the coming years. So what we can see right now is that the classical mechanics, if I take the conservation law and general relativity, the conservation law, there is something which need to be looked upon, something which was causing a problem, and this lady, Emmy Noether, was invited by David Hilbert and Felix Klein, in spite of lot of opposition, being a woman, sitting down at Gottingen University with those great mathematicians which were considered to be one of the greatest mathematicians, and solve this problem, the problem of law of conservation, which seems to be violated with the new formulation of the curvature of space-time. Now the question is that we are talking about the violation of law of conservation of energy, but is this law actually violated? If it is violated, why it is violated, where it is violated? Let us find out before going into Noether's theorem that is it the law is violated. Let us find it out in the next part of our video. First of all, what I would like to tell is that in general theory of relativity, coming along with special relativity, energy is not a quantity on its own. It is a part of the energy momentum 4 vector, which looks like this. So special relativity as well as classical mechanics, energy is not a quantity. So changing frames and changing coordinate systems can actually trade off with the energy for momentum and vice versa. Now, when we are dealing with vectors in a curved space-time, say for example this one, we have to understand that vectors actually lives at a certain space. So all these arrows, black arrows which are pointing, they're living in a certain place in space-time. Now a vector, as we know, is basically a direction of space-time which says that maybe in this direction or in that direction. Now in certain place, so a vector lives at a certain place and it is based on direction. And a vector is meaningful so that we can actually sometimes transport them to other points, but it is not meaningful to do so in all the spaces. Now let us find out that when we compare the vectors, we can always say this one is bigger, this one is smaller, and this one is smaller, and that one is bigger. But that is true in a Cartesian flat spaces. But it is always not so. But let us take an example of this kind of an equilateral triangle. When we are pointing a vector starting from the red zone, we will keep the vector parallel and we will keep moving, and our target is to come back. And here you see that the black arrow or the vector overlaps with the yellow arrow, which means that it has been actually parallelly transported. This is a technical word which I have explained in many occasions in my videos on general relativity. That means it is actually parallelly transported. Parallelly transported means starting with a position, keeping the vector parallel to the surface. If I come back, the vector will actually meet at that point. That means it has been parallelly transported. That means there is no curvature. Now if I take a sphere, I am standing here and my target is to move to this blue dot, and I am holding a sphere or a vector and I am trying to keep it as straight as possible. I name this vector as V, and I keep on moving and so on. And you see then again I am moving in this direction. My vector is parallel. So you see the direction is changing due to the curvature. Now I want to come back to this red dot point. I am coming back. And so you see that the vector which was originally at V and now at V prime, there is a sufficient difference. There is a sufficient difference. So the point is that, so it is the V and the V prime. So the point is that since the vector you get, that is the V prime, the new one, depends on the path you take, it is basically does not make any sense to talk about total momentum or total energy. Isn't it true? Because in the special relativity and classical mechanics is all depending upon the flat space time, and here we are, the entire vector is depending upon the path that we are taking. So in special relativity or even in Newtonian mechanics, as we know that the total momentum and total energy you need is just to add on. So for example, I am taking this kind of a space and these are the various points. Say for example, any kind of a space. For in case of a flat, I would do this one. This is just a kind of an example to show that I will add up all the positions from 1 to n. I will calculate the momentum. Similarly here, if I get all those things, I will do and I will calculate the total energy. So what I will do is that I will just add up the points to get the total momentum and total energy. And if you have something like a fluid, what we can do is just get an integral instead of a sum. So remember that this is possible in special or classical mechanics, or we can say in Minkowski space-time, because the transport of the vector that we are moving at is independent of the path. This means a sum or integral of momenta or energies actually yields a meaningful quantity. Now say for example, if I compare this one, that means here we can add up all the vectors and we can get the sum. But here we cannot add up the vectors. Here we definitely cannot add up the vectors, because even if we add up, we won't get back to the original vector. What is the reason for that? The reason is this. Because if I want to get the original vector back at the same point, we cannot do, since the quantity we take depends on the path that we are taking, which is not well defined. And this actually made Felix Klein doubt that if the conservation of energy, which is dependent on a particular path, on a particular manifold, on a particular place, if it is causing a curvature, if the vectors are not the same, then how we can calculate the curvature, how we can calculate the total energy, because energy in general relativity is all about the curvature of space-time. So here is the problem. Classical mechanics, we get the energy conservation by adding the total momentum and energy. But in general relativity, how can we add them? Because in order to add them, they have to be at same place. But when we parallelly transport the vector, when we come back to the original position, what we find is this, that the original and the new vector has got different directions. That means if curvature is the reason for the conservation of the creation of energy, this curvature is not the same. That means the law of conservation of energy is being violated, or there is some kind of a problem. I would like to demonstrate this fairly easily with this kind of an example. Now this one is basically what is called the stress energy momentum tensor. Let me explain this to you. This is basically what is called a covariant derivative. Now again, this is a very technical term, but to make things easy, we can call this T as a stress energy momentum tensor. So if you say covariant derivative, what it is, actually it is a derivative operator which takes at consideration the curvature of space-time. More easily, I would say, how does the difference in vectors look? That means how much the vectors are different if I parallelly transport back along the vector field. Now if I consider, say for example, this space, and these are all the very small points, right? These are very small points in which I want to calculate, for example, the amount of momentum, energy, stress, whatever. All these points, if I want to calculate, I can very well use this equation which I am showing you on the left hand side. So the stress energy tensor actually quantifies the amount of, I would say, momentum, stress and energy at every point in space and time. This equation, that is this one, which is equal to 0, says that the divergence of the stress energy vanishes at every point. What does that mean? I will just explain you. If I take a very small ball, now this is really a very small ball, and if I make the energy flow, so for example, the amount of the energy or the momentum or these things which are flowing in, it would be same as the things which are flowing out. So this is the flowing in part and this is the flowing out part, so that the total momentum is conserved. So the amount of energy momentum flowing in the ball is the same as the total momentum and amount of energy coming out of the ball. So the total divergence is 0. And that is why the total momentum is conserved. I mean to say, in classical mechanics, let us remember that we have to take this part, this ball, as infinitesimally small. Why? What will happen if I take the ball a little bit bigger? Let us look into the next part of our video. So the law of conservation of energy, what we see is that it is, in general relativity, is not conserved or seems to violate in a global scale. Why? Now you see that this is because that the gravitational field can carry energy, However, the law of conservation of energy is still conserved in the local scale, meaning that the energy of a small region of space-time is conserved. That is why I told, let us take a very small ball so that we do not expand it, and the law of conservation of energy is small, because the equation tells that the divergence is 0. Now, if I expand the ball, I make it larger. So what will happen? You see that the curvature is much larger. As soon as the curvature becomes larger, all the complication starts. So let us remember here that the effect of curved space-time start to play a role, and things starts to get more and more and more complicated. So here in general relativity, we should remember that energy is equal basically to the energy momentum tensor plus the gravitational field. This energy momentum tensor, as I have showed you a few seconds back, is actually measuring the region of space-time, provided that the region is small, and this gravitational field is actually the gravitational field itself, and this gravitational field is actually responsible for the curvature of space-time. Now you see, this gravitational field actually can fly out to anywhere, and actually it can create a problem. So what we understand till now in our video is that if I take a very small space compared to classical mechanics, I can use the stress energy momentum tensor to add up those and get the stress or energy or tensor of a specific region, so the conservation of energy is not violated. But if I expand the small object into a bigger one, the curvature of space-time comes and all the confusion starts, and the divergence is not 0, so it seems that the conservation of energy is being violated. Now this is the point when this great lady, a profound mathematician, one of the greatest thinker of our time, Emmy Noether, came in, and that is how he formulated a new theorem which saved general relativity's ship from sinking. What is that? Let us find out into the next part of our video. How Emmy Noether's theorem saved general relativity. Now, for example, if I take a star, because we know that in general relativity the space-time matrix can be curved in presence of the mass of energy. So if I consider a photon, for example this one, which is emitted, and from a star, as the photon travels away from the star, its wavelength will be redshifted due to the expansion of the universe. Now this means that the photon will eventually lose energy even though it is not interacting with matter. Right, so it will lose energy even eventually. This is just a trivial example to show you. Now what Emmy Noether so how did he solve it? So Emmy Noether's theorem actually in technical words tells that every continuous symmetry of the action of a physical system has a corresponding conservation law. Now mark it, she is actually making a very subtle I would say link between symmetry and conservation law, but that symmetry has to be continuous. In the case of general relativity, the action is invariant under time translation, which means that the total energy of the system is conserved globally. The most important point in this definition is what is called the action is invariant under time translations. Now what is that? What do we mean by action is invariant under time translation? Let us look. Very simple. Time translation or temporal transformation means that in physics, whatever the way the things are moving, the events, it is through a common interval. What does it mean? That it means that in a rigorous way that the laws of physics are the same throughout the history. Now if I take, so this is the mathematical expression. Now if I take a region, for example this kind of a region, this is a region in space-time, then if I get a time-like translation symmetry, it means that it is conserved energy. If I take a space-like translation symmetry, it means it is a conserved momentum, and if it is a rotational symmetry, that means it is a conserved angular momentum. These things I have just shown you at the beginning of the video, but however it is important, it is telling that it is a time translation symmetry. That means general relativity's all the equation will remain symmetric throughout the history. Now this equation is actually showing that the gravitational field, it is actually changing through time, where T is actually the stress tensor and G is called the Einstein tensor and K is the Einstein gravitational constant. Now you see, if I take a kind of a symmetry, for example the mirror symmetry or whatever, a symmetry in space-time. Now symmetry has got two parts. One is a discrete and a continuous symmetry. For the timing for today, this video, I would be considering what is called a continuous symmetry. Now you see that there is a deep symmetry related to the invariance of the law of physics. So Noether's theorem requires this kind of a symmetry, which you can see on the left hand side in the underlying physical laws. In the case of general relativity, there is a deep symmetry. So what it happens is that, for example, it is today, right now, what you are watching the video, the laws of physics are something, whatever be the laws of physics. Tomorrow, if you move out, the laws of physics will be the same. The laws of physics will be again the same. So what it happens is that Noether's theorem showed that even though the equations of general relativity are formulated in a way that might initially seem to challenge the conservation of energy, there is still a profound energy conservation principle at work. So here it is, the total energy of a system is conserved if the action of the system is invariant under time's translation. That means the laws of physics would be same today and it will be same tomorrow. Now this is basically a kind of a layman's definition. I am just not giving the detailed mathematics for which I will make a detailed video. So this is actually what is that. So taking the space-time symmetry, taking the continuous symmetry, Noether's theorem states that although it seems that it is not, but still the laws of physics, because it obeys the time translation symmetry, that means what it is today will be tomorrow. So for every such symmetry, this figure will give you a better understanding. For every such symmetry, there is a corresponding conserved quantity, and in this case, it is the symmetry of the time's translation, which leads to the conservation of energy. Now here is one thing we should remember. In general relativity, the total energy of a system is not just the sum of this kinetic and potential, etc. It includes the gravitational field, which changes with the curvature. So Noether's theorem shows that the total energy of a system is conserved if the action is invariant under what translation? Time translation. And this is a profound insight because it helps to maintain the fundamental principle of energy of conservation. And in this concept of Einstein's theory, it allows us and helps us to trust that universe still follows this critical law. So this is in a nutshell what Noether's theorem actually helped, saved and showed, that because the conservation of energy is being followed by time translation, hence it is preserved. But we have to remember that no theorem or no mathematical formulation is absolutely perfect. It always comes with exceptions. Now in this case, the exception is that of a black hole. So black holes actually are described by general relativity, which has got several symmetries and are crucial for our understanding. Now let us take two key symmetries for a black hole. One is the time translation symmetry, another is the rotational symmetry. These symmetries are essential because they ensure that fundamental physical laws such as the equations of general relativity remains consistent even in the vicinity of the black hole. How it is? Now see, Noether's theorem implies that the conservation of energy and angular momentum holds near the black holes also due to the inherent symmetries around the space-time. That means as particles and matter interact with black holes, their energy and angular momentum are conserved even if they approach near the black hole, near the event horizon. So because of the internal, because there is a time, there is a rotation which goes around the black hole, still the energy of angular momentum will be same. Now if I take the rotational symmetry as a whole, we know that the laws of physics are same in all directions around black hole, and if I rotate the black hole by any angle, the laws of physics will be the same. And this is what Noether's theorem tells, that for every continuous symmetry, remember it is differentiable, so it is continuous, there is a corresponding conserved quantity, and in case of rotational, if I rotate it, this corresponds to the conservation of angular momentum. So the conservation of angular momentum means that the total angular momentum of a system will remain constant in case that there is no external force or torque which is happening. So here also the angular momentum of these objects remains unchanged. And here is the final thing. The angular momentum of a black hole is conserved because the laws of physics around the black hole is same. This means that the black hole cannot lose its angular momentum by radiating or ejecting any particles away. This is very important. Noether's theorem actually is also consistent in black hole, which seems to violate the theorem. So if I take, for example, one black hole which is coming in contact with another black hole, for example, this one which is coming in contact with another black hole, and it is annihilating and creating another new black hole also, it shows that the sum of the angular momenta of the two original black holes. So when an object orbits around a black hole, its trajectory is determined by the gravitational field, and the fact that the gravitational field of a rotating black hole is symmetric under rotation follows the Noether's theorem. And Noether's theorem actually formalizes this relationship, showing that the rotational symmetry of the space-time leads to the conservation of the black hole. So now it is the time that we should summarize what we have understood in Noether's theorem. So it is a powerful tool which helps us to understand conservation laws, such as the energy, conservation energy, which seems to be violated, which we have seen in general relativity, and angular momentum, which are maintained in black holes. The symmetries are inherent in black hole space-time, which ensures that the applicability of the conservation principles. Now this is all in all what Noether's theorem is all about, which saved actually from general relativity, from the violation, and we also saw what are the different translations of symmetry and how black holes does. But what actually is the mathematical definition, what actually the Noether's theorems tell, let us find it out in the next part of our video. Now there are two theorems which actually Emmy Noether formulated. The first theorem, if I talk technically, it is something like this. There is a one-to-one correspondence between symmetric groups and the conservation law of its Euler-Lagrange equations. If I make it simple, I can tell this one. Every differentiable symmetry, now you understand it's differentiable because it has to be continuous, of the action of a physical law with conservative forces have a corresponding conservation law. Even further, we can say if a system has a continuous symmetry property, then there are corresponding quantities whose values are conserved in time. This is the first one. What is the second theorem? It is a little bit complex, but I will make it easy. Every differentiable symmetry generated by local action, there corresponds a conserved current, which is called a Noether current. To make things easier, what I can tell is that the second theorem is all about understanding what happens when you have symmetries related to the way a system changes. It says that there is a symmetry in the way a physical system changes, for example rotation, etc. There is a corresponding quantity that is conserved. So the first theorem says actually about the symmetry, that there is a symmetry, and second theorem says that when you get a symmetry, and to the way a system changes, it says that if the symmetry in the way physical system changes, then there is also a corresponding quantity. Both of them are closely related to each other, but both of them have significance. Now, in order to understand Noether's complexities of the deep, profound understanding of physics, we need a book which will give us a better understanding, a book which will be easier for us. And what is that book all about? Coming up into the next part of the video. So what is the book today? There are many books about Noether's theorem, but I would suggest to read this book. This is by Dwight E. Neuenschwander, and it is called Emmy Noether's Wonderful Theorem. As far as the customer review or the review of the book is concerned, it is 4.5 out of 5, so a fairly good amount of reviews. And these are some of the reviews which I have taken from Amazon. A delightful gem which is of model physics. It is a beautiful book. It gives about the presentation. It is self-supporting, and it is hard to find that a book would give all the necessary content. So more or less you can see the reviews are excellent, and the book actually is quite comprehensive and easy. Now if I talk of the basic table of contents, so it starts with functionals, extremals, when functionals are invariant, the invariance of fields, then it goes into invariance and phase, action as a generator, and other things. So this is basically the table of content, but most important is that the author assumes something. What is that? Let us find it out in this part of the video. So here you see I have underlined the reader that the author has a senior undergraduate physics major, and chapter 1 to 5 are quite easy. It takes an undergraduate theoretical course, but later chapters become difficult and needs a strong background in undergraduate electrodynamics. and these are quite the symbols which are being used, and these are the questions which are answered, and that's quite amazing because the author tells these are the questions which are very common, and these would be answered. What is symmetry? What is invariance? This. What are the continuous symmetry, discrete symmetries? All those things. And on the left hand side you can see these are the symbols which makes it clear. And what are the auxiliary questions? Tensors and Gauge invariance and Jacobian transformation, all those things. Okay, if I take the overall idea, then this prologue actually contains mostly about the history, how Emmy Noether got in the invitation in Gottingen, the problems that she faced, and she was appointed as an unofficial associate professor, such as an irony. And this is basically the objection which was raised, and how Felix Klein on the December 27 actually wrote to Einstein that Dr. Noether was not allowed to become a full professor, she was not paid. So it gives you a fairly good amount of history which makes the reading even more interesting. The first part starts basically with the single integral functions, and it takes beautiful examples of Fermat's principle, Hamilton's principle, and I was surprised to say it takes example from economics also. So that is quite amazing. So the author actually describes what is the formal definition of functional, and these are quite easy and you can easily go through understanding. Extremers, the Euler-Lagrange equation is covered very well. Then we come to the Hamilton's principles of the second of Newton's law. Where did Hamiltonian principle come from? This is extremely important, and the author actually emphasizes on the fact that we should know where did Hamilton's principle come from. Why kinetic energy, kinetic minus potential energy? This is also important. And what are the extremers with extreme? So this is a wonderful reading which I am sure you're going to enjoy. Then we come to why the functions are invariant, which shows that the formal definition of invariance, which shows that the Rund-Trotman identity, and it explains things very easily. Then it comes to, you see that chapter 5 actually starts with Emmy Noether's elegant theorem, but all the first 4 chapters are dedicated in making you ready, prepare, and all the mathematical prerequisites that are required. So it starts with the inverse problem, the adiabatic inference, and Noether's theorem. It starts then with part 3 with invariance of fields, which include multiple integral functions, the Euler-Lagrange equation for fields, that is very important. It is quite explicitly described with a lot of equations, examples, and all those equations are not very difficult, uses the basic calculus, etc. So I think it is quite understandable. Noethers's theorem for fields. And then the rest of the chapters, gauge invariance as dynamic principle, and then the action generator, post-Noether Noether invariance, etc. Now, if I talk this part, this underlined, this one and this one, these are a little bit, I would say, advanced concept which you can skip. I will give you an honest review. Let us look into the next part of our video. So what is the overall review? If I take the overall review of this book, then I would say, yeah, it is very well written, very comprehensive, lucid, and it actually eases the rather difficult concepts of physics. It also covers a background which gives a kind of a motivation, and these things, I would say, from gauge invariance principle and post-Noether invariance, you can easily avoid. And the good part is that the author has written it so beautifully that if you avoid it, this won't create a problem in understanding the main part, that is the crux of Noether's theorem. These examples are quite simple, and I would say the author has given multiple examples from different parts, so which becomes very clear. The mathematics is not too difficult, and the notations are very clear. Language is lucid, clear, and it makes a complete understanding of Noether's theorem. So this gives you an understanding of what the book is all about, and before that I have given a little bit detailed understanding about the problem of general relativity, what actually made Noether write this theorem, and the exceptions, and how the principles of general relativity on a global scale is not being violated using the times translation symmetry. So that's it. Thank you very much for taking up the time to watch this video. If you really like this video, please hit on the subscribe and click on the bell icon to get all the notification from Physics for Students. This is my email ID, and this is my other channel which explains much about general theory of relativity. And further, you can follow me on my Facebook, LinkedIn, Instagram, and Twitter account. Please do let me know about the comment in the comment section. What about the video? What are your reactions? How do you like it? And don't forget to subscribe. Physics for Students will be soon back with more interesting video. Till then, stay tuned and goodbye.